Hi students, today I am taking valence shell electron pair repulsion theory or Vsepr theory with some three-dimensional models. So I am taking this because you can understand better regarding especially non-planar structures and about the bond angles in the case of non-planar structures. Okay, so before going for that 3D models, at first we can take few postulates regarding Vsepr theory. I have not taken all postulates here, only 4 postulates I have taken. In that, first one is the shape of molecule depends upon the number of valence shell electron pairs, it can be bonded or non-bonded, around the central atom. Okay, the first postulate says if we take any molecule and the shape of that molecule depends upon how many electron pairs are present in the valence shell, and electron pairs means it can be a bonded or non-bonded electron pair. So the shape of molecule depends on the electron pairs present in the valence shell. That's the first postulate. Let us go for second one now. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. Okay, so we already know like charges repel each other, unlike charges attract each other, right? The same concept here. The pairs of electrons, you know, it's negatively charged, right? Electron clouds, so there will be a repulsion between the electron pairs. Next one now. Third postulate is these pairs of electrons tend to occupy such positions in space that minimize the repulsion and thus maximize the distance between them. Right, now if we take electron pairs, bonded as well as non-bonded, how they arrange themselves around a central atom. So they arrange in such a way that there should be minimum repulsion and maximum distance between them. Okay, so there should be minimum repulsion and maximum distance. Okay, so in that way the electron pairs get arranged around a central atom. Right, that's the third postulate. And the fourth postulate is regarding interaction or repulsive interaction between electron pairs. So oddly taken, right, electron pair can be taken as bonded or non-bonded electron pair. Non-bonded can also be taken as a lone pair of electrons, right? So the interaction we can take like 3 types. A bond pair may interact with bond pair may interact with a lone pair, and a lone pair interact with another lone pair. So the repulsive interactions we can take in the order of lone pair should be more than lone pair, more than bond pair. Okay, that's the repulsive interaction order, okay, decreasing order. Right, this is regarding a few postulates of Vsepr theory. The next one is, if we take molecules now, or can take prediction of geometrical shapes for the molecules by applying Vsepr theory, we can divide molecules in 2 categories. First one is molecules in which the central atom has lone pair of electrons, no lone pair of electrons, and the second one is molecules in which central atom has one or more lone pair of electrons. So we can take 2 here, right? Molecules in which central atom is having no lone pair of electrons, and the second type of molecules are having lone pair of electrons around central atom. Okay, so in this session or video, I have taken only the first type. Okay, because I couldn't complete all the molecules because I'm taking 3D models. So I split it actually, okay, as part 1 and part 2. So in this video we are taking only molecules in which central atom has no lone pair of electrons. Now let us take a table. Right, this table shows or gives examples also. The geometry of molecules in which central atom has no lone pair of electrons. Right, so no lone pair of electrons here. Now number of electron pairs can be taken as 3, 4, then we are having 5 and 6. Let us take one by one now. If any central atom is having 2 electron pairs around that, What's the arrangement of electron pairs? You know the rule, right? Third postulate says there should be minimum repulsion and maximum distance, right? Now how these electrons arrange themselves around atom A here? So it should be in a linear fashion, right? So what happens? Arrangement should be linear, and the geometry, we can take molecular geometry as linear. Okay, so this can be taken AB2 molecule. Okay, example, what I'm going to take is BeCl2. We can take three-dimensional model for that, beryllium dichloride. Okay, so BeCl2 can be taken as an example for a linear molecule. Now the second one, with the number of electron pairs 3. Now if you take 3 electron pairs, arrangement should be trigonal planar. You know, if you're having a bond angle of 120 degree, then only the electron pairs will be having minimum repulsion and then maximum distance. Okay, so the arrangement of electron pairs will be trigonal planar, and the molecular geometry should also be the same, right? Because no lone pair of electrons here, so it should also be the same trigonal planar with a bond angle of 120 degree. So one of the example for that is boron trifluoride. So BF3 can be taken, right? Okay, now if we take number of electron pairs around a central atom as 4, and as no lone pairs, all 4 should be bonding pairs of electron, right? Okay, you can see the arrangement first here. We can arrange 4 pairs of electrons around A, and arrangement has to be a tetrahedral arrangement with bond angle of 109.5 degree or 109 degree 28 minutes. Okay, so the geometry, molecular geometry is tetrahedral. And example, we can take methane or we can take ammonium ion. Right, next one, if you're having 5 electron pairs around a central atom, arrangement has to be, you can see this arrangement, we can take it as trigonal bipyramidal. We can take even as TPP also, right? You know why it is named as a trigonal bipyramidal? You can see the base here, right? So this is trigonal shape, right? Trigonal shape, and you can see one pyramid above and one pyramid below here, right? So it is given as trigonal bipyramidal. And if you take this plane, what I shown here, between the bonding pairs, we got angle, right? Bond angle is 120 degree. And if we take these 2 electron pairs now, so what happens there? It creates a bond angle of 90 degree with the plane. Okay, I'll explain once again while taking the 3D geometry. So the 2 bond angles will get in the case of TBP geometry. One is 90 degree and other is 120 degree. Right, so this is molecular geometry, trigonal bipyramidal, and one of the example is PCl5 can be taken. Right, the last one is with 6 electron pairs. So if you're having 6 electron pairs around any central atom, the arrangement of electron pairs should be octahedral. You can see here, right? Again, these 4 electron pairs in one plane, and you can take these 2 now above the plane, and this you can take it as below the plane. Okay, here also you can expect bond angles. In the plane we'll be having one angle there, 90 degree, and with the plane, okay, these 2, one above the plane and one electron pair below the plane, creates an angle of 90 degree. So octahedral geometry will be having only one bond angle, that is 90 degree. Okay, so this they are given molecular geometry as octahedral, and one of the example can be taken as SF6. Right, so in this way we take some examples for, or can take guessing geometry of molecules in which central atom is having no lone pair of electrons. Right, now I have taken few examples here like BCl2, BF3, then I have taken methane, PCl5 and SF6. Okay, so let us move for 3D geometries now, okay, for these examples. Okay, let us start with first example. So in the table you saw the first molecule is AB2 type molecule, and example is BeCl2. So if you take AB2 type of molecule, we'll be having arrangement of electron pairs linear, as well as molecular geometry is also linear with bond angle of 180 degree. Okay, so this is BCl2 molecule, okay, with bond angle of 180 degree. Okay, so let us go to the next example now. The next example is of the type AB3. And if you take AB3 type of molecule, you can take the best example is boron trifluoride, BF3. And in the case of BF3, you can see this is planar geometry. A reason for that, you can see all atoms in the same plane, right? So it is said to be a planar geometry with a bond angle of 120 degree. So we got three 120 degree bond angles in the case of boron trifluoride. So we can take the molecule in this way. So this is about boron trifluoride. Remember, the bond angles are we got 120 degree angle here. Okay, next molecule is of the type AB4. And if you take AB4 example, I taken as methane here. Around central atom, that's carbon, we got 4 hydrogen atoms, right? So it's having 4 bonding pairs of electrons around carbon. And the geometry, we can take it as tetrahedral geometry with bond angle of 109 degree 28 minutes. So you can see some angles given as 110 here, so that should be corrected. It should be 109 degree 28 minutes. Okay, so the geometry, we can call it as tetrahedral geometry. Right, next one is PCl5, phosphorus pentachloride. Okay, this is of the type AB5, and I got many times a question asked based on the molecular geometry. They can even ask like how many bond angles are present. Okay, so the bond angles also very important here. So you can see this geometry is TBP or Trigonal Bipyramidal geometry. So at first, let me take a plane. Okay, this is a plane, right, which contains 1 phosphorus and 3 chlorine atoms in the plane. And in the plane, you can see some angles there, right? We got 3 120 degree angles in the plane of Trigonal Bipyramidal geometry. Okay, so this is in the plane. Now we got 1 chlorine above the plane and another chlorine below the plane. Okay, so what it does now, this chlorine, it creates 90 degree angle. How many possible? Let me rotate the molecule so you can see it clearly now. Above this plane, we can see 3 90 degree angles, right? And below the plane, we can see again 3 90 degree angles. So in the case of Trigonal Bipyramidal geometry, we are having 3 120 degree angles in the plane and 3 plus 3, right? 6 90 degree angles okay, you can take like collectively, right, in the molecule. So totally 3 120 degree and 6 90 degree angles are present in the case of phosphorus pentachloride, or you can take Trigonal Bipyramidal geometry. Okay, right, this is regarding PCl5. And the last molecule is sulfur hexafluoride. Right, now if you take sulfur hexafluoride, this is again having a plane, right? Let me take that again first. So this is a plane now which contains sulfur central atom, then you got 4 fluorine atoms, right? Okay, this makes one plane, and you can see some angles, right? Only the 90 degree angles, we got 4. Okay, and 1 fluorine above the plane, another fluorine below the plane. So totally we got 6 fluorine atoms, right? And you can easily count the number of 90 degree angles now, as it contains only 90 degree angles. Okay, there is no 120 degree in the case of the geometry. We can take it as octahedral geometry. Okay, and this is a molecule of the type AB6. So just count number of angles now. In the plane, we got 4 90 degree angles. This above fluorine, it's creating totally 4 90 degree angles, right, with the plane. And this fluorine also creating totally 4 90 degree angles. Okay, so totally we can take 4 plus 4 plus 4, right? 12 90 degree degree angles are present in the case of sulfur hexafluoride. Okay, right, this is a molecule, sulfur hexafluoride. Okay, so that's about the first part of Vsepr theory. In the second part, I'll be covering few more molecules, like the molecules with lone pair of electrons. Okay, right, if you like the video, please subscribe to my channel. Thank you.